Today we're going to chat about the Haber process and the contact process. Let's start with the Haber process. This process is also known as the Haber-Bosch process, and it's an industrial method that's used to produce ammonia. Now we use nitrogen and hydrogen gas to do this. It's one of the most important chemical processes in the world because ammonia is essential for fertilizers, which support global agriculture. Now, in the Haber process, we need a few types of equipment. The first one we need is a compressor. Now, this compressor is able to compress the gas into a more concentrated form. We then have a reactor, which contains an iron catalyst, and this helps speed up the reaction as well. Lastly, we have the condenser, and what a condenser does is it cools down the products so that some of them can form liquids. Now for this process, we use hydrogen and nitrogen gas. Now the hydrogen gas is obtained from methane, and the nitrogen we get from our air. Now these two gases are pumped into the compressor through a pipe. Inside the compressor, the gases are compressed to around 20,000 kilopascals or 200 atmospheres. The pressurized gases are then pumped into a tank containing an iron catalyst. Here the reaction will happen at 450 degrees Celsius. Now some of the hydrogen and nitrogen react to form ammonia, but some does not react. The unreacted hydrogen and nitrogen and the ammonia product will pass through the cooling tank or the condenser. Unreacted hydrogen and nitrogen gas are then recycled back into the system and it all starts over again. Here the ammonia will be liquefied and can be removed to a pressurized storage vessel. Now the reason why we remove the ammonia is by decreasing the concentration of the products, we increase the rate of the forward reaction. Now, as in all industries, companies that manufacture and sell chemical goods do so to make a profit. So part of the industrial process is the economic decisions on how and where to design and implement a manufacturing site. So the availability and the cost of raw materials is a major consideration, which must be studied well before any decisions are taken. Now in the Haber process, the raw materials are readily available and very inexpensive to purify. This is because we get nitrogen from the air and hydrogen from natural gas called methane. If the cost of extraction of raw materials is too high or they are unavailable, then the process is no longer economically viable. So many industrial processes require huge amounts of heat and pressure, which is very expensive to maintain. The production energy costs are also a factor to be considered carefully. Now there are three variables to consider when doing this reaction. Now sometimes the conditions that we choose are contradictory. So we have to make choices between the factors to improve the yield of ammonia and those that speed up the reaction. So let's look at the reaction. We have nitrogen plus hydrogen that gives us ammonia. The first variable that we will look at is temperature. Now we know that this reaction is exothermic, meaning that the forward reaction will be exothermic and the reverse reaction will be endothermic. Now when we increase the temperature, the reverse reaction will be favored and more of our reactants will be made. But if we decrease the temperature, then the forward reaction will be favored, meaning that we yield higher amounts of products. But if we lower the temperature, it also decreases our rate of our reaction. So we need to compromise. For this, scientists have chosen 450 degrees Celsius as a compromise temperature between lower yield of the product being made and increasing the rate of the reaction. The second variable that we'll have a look at is pressure. For this, we need to know the amount of gas molecules as reactants and as products. So here we can see that we have 1 mole of nitrogen and 3 moles of hydrogen. So that's a total of 4 moles of reactants. And we have 2 moles of ammonia. So that's 2 moles of products. Now at a high pressure, the reaction would want to favor the side with the least amount of gas molecules. This will be the forward reaction. But at a high pressure, it's also very dangerous and it is expensive as it costs a lot in electricity and an equipment to increase the pressure. On the other hand, a low pressure favors the reverse reaction, which means that more reactants will be produced. So for this, we need to compromise. This compromise is 200 atmospheric pressure. This is a compromise between a lower yield of products being made and then also our safety and being more economical. So the last variable that we will look at is a catalyst. Now, the presence of a catalyst does not affect the position of the equilibrium, but it does increase the rate at which the equilibrium is reached. This is because a catalyst increases the rate of both the forward and the reverse reactions by the same amount, and it does this by providing an alternative pathway that requires a lower activation energy. Now, as a result, the concentration of the reactants and the products is nevertheless the same at the equilibrium as it would be without a catalyst. But using a catalyst allows us to achieve an acceptable yield at a lower temperature by lowering the activation energy. Without a catalyst, the process would have to be carried out at an even higher temperature, increasing the cost and decreasing the yield, as the higher temperature decomposes more of the ammonia molecules into nitrogen and hydrogen gas. So the catalyst that we use in this reaction is iron. The next process that we're going to have a look at is the contact process. And this is the industrial method used to manufacture sulfuric acid. This is one of the most important chemicals in the world. Sulfuric acid is used in fertilizers, detergents, paints, batteries, and in a lot of industrial processes. Now, for us to manufacture sulfuric acid, we need a few equipment again. So the first thing that we're going to need is a furnace, and this is used in stage 1 of the contact process where sulfur dioxide is produced. We then also have a converter that has vanadium 5 oxide catalyst in it as well. This will increase the rate of the reaction, converting sulfur dioxide to sulfur trioxide. This is also the main stage of the reaction. Then lastly, we need an absorber. Here we use sulfuric acid and sulfur trioxide to form oleum, which is disulfuric acid. This is then converted to sulfuric acid. So in this process, we have 3 different stages. In the first stage, we produce sulfur dioxide. We do this by using oxygen and sulfur. We burn the sulfur and oxidize it into sulfur dioxide. We can also do this process by roasting sulfide ores to form sulfur dioxide. The sulfur dioxide is then pumped to stage 2. And this is, like I said, the main stage in the oxidation of sulfur dioxide to sulfur trioxide. And here we use the catalyst vanadium 5 oxide. So oxygen here is used and it's obtained from the air. Here the reaction must be kept at 450 degrees Celsius and 2 atmospheric pressure, or 200 kilopascals. The sulfur trioxide is then moved to stage 3. Here it's absorbed into a solution of 98% sulfuric acid, and this produces a thick liquid called oleum. Now, oleum is disulfuric acid. The oleum is then added to water to form a concentrated sulfuric acid, which is then collected and stored. Just as in the Haber process, the contact process also has variables to consider. So remember, we're only going to look at the main stage of the contact process, where sulfur dioxide and oxygen reacts to form sulfur trioxide. Now, the first variable that we're going to look at is temperature. This reaction is exothermic, which means that the forward reaction will be exothermic and the reverse reaction will be endothermic. So if we have a high temperature, it will favor the reverse reaction, that is endothermic. So a higher yield of reactants will be made. But if we use a low temperature, it will favor the forward reaction because this reaction is exothermic. So a higher yield of products will be made. But just as in the Haber process, a low temperature will decrease the rate of the reaction. So yet again, we have to compromise. And the compromise for this reaction is 450 degrees Celsius, which is a compromise between having a lower yield of products being made and being made more quickly. So the second variable that we're going to have a look at is pressure. Now, again, for us to understand how pressure affects this reaction, we have to look at the amount of moles. So for our reactants, we have 2 moles of sulfur dioxide and 1 mole of oxygen. So this gives us a total of 3 moles of reactants. For our products, we have 2 moles sulfur trioxide, so a total of 2 moles for our products. So if we increase the pressure of the reaction, it will favor the forward reaction because there's fewer moles of gas product. So a higher yield of products will be made. But this is also very dangerous and very expensive. So at a low pressure, it will favor the reverse reaction because there is more moles of gas molecules in the reactants. So a higher yield of reactants will be made. So we need to compromise. We would think that they would choose kind of a high, maybe like in the previous Haber process, 200 atmosphere. But no, they chose 2 atmospheric pressure. The reason for this is because the equilibrium mixture already contains about 96% sulfur trioxide, which means that the equilibrium lies far to the right. High pressures can also be dangerous and expensive because electricity and equipment to keep the high pressure is expensive. And the last reason is because a high pressure can cause the sulfur dioxide to liquefy, and it will then not react with the oxygen. So we use a low pressure. The last one that we're going to look at is a catalyst. Now, just like in the Haber process, the catalyst will increase both the forward and the reverse reactions. Now, for the contact process, we use vanadium 5 oxide as a catalyst.